Today we'll look at some circuits for improved current sources. We started early in the semester, we discussed some simple current source circuits, current mirrors, and we know about their characteristics and how they're implemented using MOSFETs or bipolar transistors. So we'll see how we can improve the characteristics of the current sources we started with. So what are we going to improve? First, the output resistance. The ideal current source has an infinite output resistance. If I have a current source with a relatively small output resistance, I want to make it larger. So that would be an improvement because I will be going in the direction of the ideal situation. So the current should be less dependent on the voltage across the source. The second thing is the parameters of the transistors in the circuit may affect the value of the current source and the current source. And there may be a way around that, but what if these parameters also vary, such as beta and the BJT, which may not be constant. If I change the transistor, I'll get another beta. If I move from one location to another, I will get another beta. If temperature rises, beta will change. So if the expression of the output current has beta in it, that would not be good news. And I want to maybe improve on this, make the current less dependent on such parameters as beta of the BJT. So these are the two main goals. But we will see that to achieve the goals, we'll have to sacrifice something. And what we will sacrifice is the simplicity of the circuit. The circuit will have more transistors, will be more complicated, more complex. And also the voltage range, the minimum voltage that can appear across the source, this would be higher now. So let's review first the basic MOSFET current source circuit. We had two MOSFETs and a resistor, or in the case of a reference current, I would have a reference current source in place of the resistor. Well, that's the basic circuit. Two MOSFETs, one of them with drain shorted to gate, a resistor, some supply VDD, and here, this is where I have my output current. So this circuit, as far as the rest of what I have is concerned, this circuit is like a current sink. It forces a current IO to flow out of the rest of the circuit. So this is the rest of the circuit. And this I out is constant or almost constant. So this is a simple current source, or as we called it, a current sink. And IO depends on the ratio W over L2. So this is MOSFET 2, this is MOSFET 1. A simple expression for IO would be W over L2 divided by W over L1 times the current in the resistor. And the current in the resistor is determined by this part of the circuit, and therefore not affected by what happens on this side in the rest of the circuit or in M2. and we can consider it to be constant. So constant times constant divided by constant, and the output current is constant. For this to work, however, M2 should be in SAT. And if M2 should be in SAT, it means that VO, which is VDS2, this is the condition for SAT for M2, and VDS2 is VO, the voltage at the output node here, we call it VO, should be greater than VGS2 minus VT is this VGS, which is common to the two MOSFETs, minus VT, we call this quantity VOV. And that's usually a fraction of a volt, maybe 0.2, 0.3, 0.4, 0.5 volt. So the voltage at the output node has to be greater than that. So the voltage at the output node cannot drop below, let's use 0.5 volt for VOV. That's typical value. So the output here, the potential here at this node cannot drop below 0.5 volt for this to work. The other thing, so this is a limitation. This is a limitation. In an ideal source, I don't care what the voltage is, the current will be the same. The voltage can be 0.5, less than 0.5, greater than 0.5, positive, negative. The current that will flow will be the same. So if I have an ideal source like this with a current I don't care what V is. It doesn't matter. Can be anything. The current that will flow here in this branch will be I. That's the ideal case. In our case, the current is constant or almost constant, but the voltage cannot be anything. It has to be greater than 0.5 volt. The other limitation is that the current is not really constant. It increases when VO increases. So if VO is greater than 0.5 and it's 1 or 2 or 3 volt, we will actually get an increase of IO with VO. And this is due to the, in the case of the MOSFET, due to lambda, due to channel length modulation. So MOSFETs have a certain lambda, which is not 0. And the output current is the drain current, and the drain current increases with VDS. So this is the term 1 plus lambda VDS in the current equation. And this means that IO will increase with VO here. IO will not be fixed. So if VO is greater than VOV, we will get a current IO that is almost constant, but not really constant. And we measure how bad the situation is or how good the situation is by the output resistance, which is delta VO over delta IO. And this means that delta IO is delta VO over RO. And I want this ideally to be 0. Delta IO is how much the current changes. So ideally, should be 0. It should not change. IO should not change. And its delta should be 0. But actually, I will get a certain delta IO in this case. And for this particular circuit, big RO is equal to small RO2. And small RO2 is maybe tens of kilo ohms. So if I have a delta VO and let's say 2 volt, RO2 of M2, small RO2 of MOSFET M2 is 20K. The increase of 2 volt in VO divided by 20K will give me how much the current will increase. So that's 0.1 milliamp. So VO is greater than 0.5. So let's say it increases from 1.5 volt to 3.5 volt. That's a delta VO of 2 volt. Small RO2 is 20K, and I get a delta IO. So IO is increasing by 0.1 milliamp, and therefore it's not exactly constant. How do we fix this? Make RO bigger. Make this as large as possible. So the larger the RO, the better, because it appears here. If I want to make this ideally 0, I want to make this go to infinity. Ideally, infinite. So today we'll see how we can make RO larger. In the case of the bipolar, we had a similar circuit, but with bipolar transistors and equations that are similar, but with a small issue concerning the dependence on beta. So this is the BJT version of the circuit. And we derived the equation, and we got something like IO here, even if I don't consider any early effect, is the reference current in the resistor times 1/1 plus something like 2 over beta. This term did not exist in the MOSFET circuit because there's no gate current in the MOSFET. Because the BJT has base current, so there is a base current here, there is a base current here, and there's twice the base current here, I get this 1/1 plus 2 over beta. And this means that if everything is exactly matched, IO will not be exactly equal to IRF. There is this difference. And what makes this really annoying is that beta may not be fixed. And it may vary, for example, from say 20 to 150, depending on the circuit, the BJT in the circuit, depending on the temperature in the circuit, depending on the manufacturing. Beta is not a constant number. So 20 to 150, this means that IO would be so what is this? 1 plus 2 divided by 20, and then 1 over x. This is 0.91 IRF. 2, if it's 150, 2 divided by 150 plus 1, and then 1 over x to 0.987 IRF. So here's the thing, it's not 1. IO is not exactly IRF. That's the first problem. The second problem is it can be 0.91 IRF or 0.99 IRF, depending on the beta that you have. So today also we will see how we can fix this. Hopefully we can fix this dependence on beta that makes the output current not just less than the reference current, but also in a range which is large. The range here is like, was it 10% variation or 9% variation? Maybe we can make this variation much smaller. Here's an improved bipolar current mirror. And you see here the inclusion of this additional Q3. So I have an extra BJT Q3 here. So let's see how this helps. The two transistors Q1 and Q2 have the same VBE, and we will assume that they're identical, they're matched, they're exactly the same BJT, and they have the same VBE. So as a first order approximation, we will say that if they have the same VBE and they're identical, their collector currents would be equal, of course, in the active region. So this is IC here in Q2 and IC in Q1. And since they're inactive, then the base current of Q1 and Q2 will be IC over beta, IC over beta. The sum by KCL is a current flowing down, and that's the emitter current of Q3 to IC over beta. So IC over beta plus IC over beta flowing down by KCL would be 2 IC over beta, but this current is flowing down from the emitter of Q3. Q3 should also be in the active region. And if this is the current in its emitter, then the current in the base of Q3 would be 2 IC over beta, the current in the emitter, divided by beta plus 1. So 2 IC over beta divided by beta plus 1. Now, this current plus this current is equal to IRF by KCL at node X. So the current here, IRF, is IC plus 2 IC over beta into beta plus 1. So that's IRF. The output current is IC, just IC. So IRF is this, IO is IC, and IO over IRF would be 1 over 1 plus 2 over beta squared plus beta. So now you see that the dependence on beta changed. It was 1 over 1 plus 2 over beta. When we add Q3, it becomes 1 over 1 plus 2 over beta squared plus beta. So the error term, what we call the error term, is almost 2 over beta squared here. So let's see, is this an improvement? Let's repeat the calculation we did when beta varied. If beta is 20 to 150. When we did not have a Q3, the output current changed from 0.91 IRF to 0.987 IRF. 0.910 IRF to 0.987 IRF. So both less than 1 and with a large range, relatively large range. If I use this equation now with beta 20 to 150, what do I get? So, okay, here's 20 times 20 plus 20, and then 2 over that. So 2 over plus 1, and then 1 over. So 0.995, when beta is 20, this is 0.995. And when beta is 150, this will be times 2 plus 1, and then 1 over 0.9999. So 1, almost 1, to 0.9999. So 2 improvements here. The first is the range is closer to 1, very, very close to 1. So instead of 0.91 to 0.987, now it's 0.995 to 0.9999, very close to 1. And the other thing is the variation. Instead of getting 8%, 9% variation, now it's more like 0.5%. So the output current is very close to IRF and does not change if beta is different, is changing. So this makes the dependence of IO on beta much smaller. IO is no longer sensitive to variations in beta. So that's an improvement. the dependence on beta because of this beta squared is less. Beta is a large number, and this is what we're relying on now. Because it's large and the error was 2 over beta, if I make the error 2 over beta squared, and beta is large, and that's a big improvement. But the output resistance is still the same. The output resistance here, looking into the drain of Q2, is still small RO2. So there's no improvement in the output resistance. It's still small RO2, so delta IO is still delta VO over small RO2. I did not improve the output resistance. And the voltage range, the VO minimum here, is still VCE edge of sand. VO min for the BJT case is when Q2 reaches the edge of saturation. So that's like 0.3 volt VCE edge of sand. In the MOSFET case, it was VOV. In the BJT case, it's VCE edge of sands, which is like 0.3 volt. And this did not change. When I added Q3, it did not affect this limit. So I kind of improved one that depends on beta. I did not improve 2. So this is checked, but this did not improve. And the voltage range did not change. So this is kind of check. I did not throw in the voltage range. I can't make it smaller. It's 0.3 volt is the limit. But we'll see now a circuit where this becomes larger. And it means that it got worse. So I improved the dependence on beta without improving the output resistance. The next circuit we will see would improve also the output resistance. And it was an interesting circuit when it was introduced because it also uses 3 transistors. So there was a kind of a challenge among circuit designers that is there a circuit that can improve the dependence on beta, so make the output current less sensitive, and at the same time improve the output resistance, but only use 3 transistors. Because if you want to use 4 transistors, it's very easy. But using 3 is tricky. But it was possible. This designer called Wilson came up with this circuit that has 3 transistors and that improves the dependence on beta and the output resistance. So let's follow the currents. Again, we start here with Q1 and Q2 having the same VBE. And if they have the same VBE, then as a first order approximation, they will have the same IC. Again, they are matched and identical, not just matched. Notice that Q1 is now the BJT that has the short between base and collector. So that's different from the mirror circuit, the simple mirror circuit where the short was on the other side. All right, so IC here, IC here. The base currents would be IC over beta and IC over beta. Then by KCL, this current would be IC over beta plus IC over beta. So 2 IC over beta. Let's move to this node and do a KCL here. The current flowing here would be IC plus 2 IC over beta. So IC into 1 plus 2 over beta. And this happens to be the emitter current of Q3. Again, Q3 must be in the active region. So its base current would be its emitter current which is this, over beta plus 1. So that's the base current of Q3. The collector current would be beta times this. So you take this quantity multiplied by beta, and this is the collector current of Q3, which is the output current. I am taking the output from the collector of Q3. Going back to this node, IRF is the current flowing here, and it's equal to the current flowing here, which is IC, plus the current flowing here, which is this expression. And therefore, IRF would be equal to this, the sum of these two currents. So finally, I can take the ratio IO over IRF, and I get this expression, but it can be simplified to this 1 over 1 plus 2 over beta into beta plus 2. And that's great news. Why is it great news? Because beta is large, and beta plus 2 is large and almost equal to beta. So this is almost beta squared. And therefore, because I see a beta squared with beta a large number being a large number, the error is very small. So the output current would be almost equal to the reference current, very, very close to the reference current, and it doesn't vary much if beta varies. So that's an improvement, and that's similar to the circuit on the previous slide. But the other improvement here is also in the output resistance. If you calculate the output resistance of this current mirror, it's a long calculation actually. So we will not go through all the steps, but you can show if you do this calculation by replacing the transistors by their small signal models and doing Vx over Ix, that the output resistance is beta times small RO over 2. So it's beta over 2 times bigger. Previously, it was small RO. Now it's beta over 2 times bigger. So it means that it's at least 10 times bigger, and it can be 100 times bigger. So much bigger output resistance than before, and therefore much smaller variation in the output current than before. So dependence on beta decreases, output resistance multiplied by beta over 2. Excellent. The price we pay is the reduced range. So the voltage here at the output node, this voltage cannot be too small. Definitely cannot go to 0.3 volt, as was the case on the previous slide. Why is that? Well, the voltage here at the collector of Q1 is the same as the voltage at the base of Q1. And Q1 is active. And when a BJT is active, VBE would be around 0.7 volt. So the voltage here, there is a drop of 0.7 volt here. And the voltage at the collector of Q1 would be minus VEE plus 0.7 volt here. And then Q3 must be inactive, and it cannot have a VCE which is less than 0.3 volts. So this VCE for Q3 should be greater than 0.3. So here I have 0.7 volt plus minus, and here I should have at least 0.3 volt. So VO therefore should be at least 1 volt larger than minus VE. And if this is ground, then VO should be at least 1 volt. So now I have a reduced range for VO, because it cannot drop below 1 volt. It means that I lost in voltage range. In the previous circuit, a VO of 0.5 would be okay. A VO of 1 would be okay. A VO of 0.8 would be okay. 0.9, 0.7. Now, a VO of 0.8 would not be okay. 0.5, definitely not. 0.7, 0.9, 1 and higher. So this is the price that we pay to get less dependence on beta, much better output resistance. We lose in the range of VO. So this is the Wilson current mirror, and there is a MOSFET version of it that I will show very quickly here. This is the Wilson MOSFET version, and you can show through small signal analysis that the output resistance is much bigger than before, so GMRO times. And of course, there's no beta here to show that there is less dependence on beta, but the output resistance definitely is much higher. The price we pay, again, reduced range of VO. I should maintain a higher VO. And this is what we call a balanced Wilson MOSFET current mirror. But now we're using 4 MOSFETs. So 4 transistors, not 3. And if I need to use 4 transistors, maybe I can use something that now I'm more familiar with, which is the just cascoding. We know that cascoding increases the output resistance, and I can build the cascode with 4 MOSFETs. So why not use just cascoding and do something like this? And that's a cascode current mirror. So this is Q1 and Q2. This is the simple current mirror that we are familiar with. Now Q3 and Q4 provide the right bias here and the cascoding effect. Q3 provides the cascoding effect, and Q4 provides the right bias for Q3. So this is the V bias 1, and this is V bias 2. These are DC voltages. And Q2 and Q3 are just a cascode pair. And we know we have a rule that if you're looking into the drain of a MOSFET with no signal at its gate, and another MOSFET is connected between the source terminal of the first one and ground, and also it has no signal at its gate. So checking the formula sheet for resistance calculation, we have a circuit like this, and this is the resistance that we see looking into the drain of Q3, RO2 plus RO3 plus GM3, RO2, RO3. And that's great news, because by adding Q3, the output resistance increases by, say, RO2 and RO3 are almost equal by something like 2 plus GMRO, which can be quite large. So that's an output resistance which is tens of times bigger than what I had. That's a great improvement. But again, we lose in voltage range. This VO cannot drop now to VOV. There's a higher limit on VO now. VO min is now VT of the MOSFET plus 2 VOV. It was just 1 VOV. So if VT is 0.7 and VOV is 0.5, now it's like 1.7 volt when it was 0.5 volt. So it has to be higher than 1.7 or 1.5 when it was just 0.5. Why is VO min VT plus 2 VOV? Well, let's look at the gate voltages. This voltage here, V bias 2, is VG of MOSFET 3. And VG of MOSFET 3 is this VGS, right, plus this VGS. So this plus this, are two VGSs, and there is a short from here to here. So this VGS plus this VGS is VG3. So VG3 is therefore 2 VT plus 2 VOV. VGS, one VGS is VT plus VOV. Two VGSs is 2 VT plus 2 VOV. Now, the condition for Q3 to remain in saturation is VDS greater than VGS minus VT, or VD greater than, so for Q3, VD3 should be greater than VG3 minus VT. What is VG3? It's 2 VT plus 2 VOV. So this is here, and therefore this is 2 VT minus VT, VT plus 2 VOV. And VD3 is exactly VO, because the output is taken from the drain of Q3. So VO min is therefore VT plus 2 VOV. That's the minimum voltage at the output node. This is the voltage that was VOV. Now it's 2 VT plus, VT plus 2 VOV. Woodler current source is another improved current source that allows us to have small output currents without using very large resistors. So here in this case, I add this RE resistor between the emitter of Q2 and ground. And when I do this, I break the equality. Now VBE for Q1 is no longer equal to VBE for Q2, because this is VBE1 between the base and emitter of Q1, so it's all the way to ground. VBE2 is between the base of Q2 and the emitter of Q2. But I can still write a relationship. I can have a relationship between them, because the current in R2 is the emitter current of Q2. So VBE1 is VBE2 plus IE2RE. And Q1 and Q2, if they're inactive, there is a relationship between IC and VBE that I can use now. VBE is VT log IC over IS plus 1. This comes from the equation in active that IC is IS e to the VBE over VT minus 1. So VT log IC over IS would be equal to VBE. VBE1, therefore, is VT log IC1 over IS plus 1 equals VBE2, which is VT log IC2 over IS plus 1 plus IE2RE. I will make now an assumption that the currents are much larger than IS, and that should be the case. IS is extremely small, so I can neglect the plus 1. And the other thing is I will assume that this is equal to IC2, which is kind of okay if beta is large. If beta is large, I can assume that IC2 is almost IE2. So rearranging the terms, I get VT log IC1 over IC2 equals ICRE. Again, if beta is very large, IREF, the current here would be almost 0, because it's the sum of these two currents which are negligible. So IREF is almost IC1, and IO is exactly equal to IC2. So I get this equation. And from this equation, if I want a certain output current, and I have IREF, this allows me to select the value of RE. So I want, say, a certain output current, 10 microamp, and I have a reference current which is 100. This allows me to select the value of RE that I need to insert here. Remember, this current source helps when I want an output current which is small compared to the reference current that I have. So I may have a reference which is 100 micro or 1 milli, but I need a much smaller current. I need maybe 20 micro. This is a very nice way to get this by adding a resistor here. So you get VT. Let's use 1 milli and 20 micro. VT ln 1000 over 20 is equal to 20, so 0.02 times RE, and VT is 25 millivolt, and this is 0.02 milliamp. So you can solve this and you get the value of RE that you need to get the small output current. Another advantage of inserting this RE is actually raising the output resistance. So that's nice. We insert the RE to get the small output current, but at the same time, it helps in making the output resistance bigger, because if you're looking into the collector of a BJT, and there is a DC voltage at the gate, at the base, excuse me, and a resistor RE between emitter and ground, there's a formula for that in the formula sheet. And you get an output resistance which is almost 1 plus GM RE parallel R pi times RO. So this is definitely larger than 1. And the output resistance is definitely greater than just small RO when I did not have the RE. So this nice trick of adding the RE between the emitter of Q2 and ground would allow us to have small output currents and at the same time a larger output resistance. And this circuit was designed by Woodler, one of the most famous analog circuit designers ever. Woodler is credited with the design of the integrated circuit op amps